principle of moments. So let's think about a seesaw with a person sitting on either side, but one of the people is further away than the other. So this will be person A, and this would be person B. And let's suppose that they are of equal mass. Which way is the seesaw going to turn? Well, in this case, you can probably guess that it's going to turn this way. It's going to turn anti-clockwise. And you'd be right. And the reason for that is because of the principle of moments. The principle of moments says that the turning effect of a force depends on two things. It depends on the size of the force and the distance that the force is from the pivot. Force times distance. What we have a strange word for this. We call it the moment of a force, and we work that out as force multiplied by distance from pivot. So if we come back to our example here, you can see that weight A is going to create a bigger moment than weight B because it's at a greater distance from the pivot. If we want our beam then to be balanced, then to get equilibrium or balance, the clockwise moment of the force has to be equal to the anti-clockwise moment. So in this case, to get balance, to get equilibrium, because A is at a greater distance from the pivot, we'd need B to be heavier. If we want to do an equation for that, we could call the force and the distance on one side F1 and D1, and we could call the force and the distance on the other side F2 and D2, where these are the sizes, F1 and F2 are the sizes of the forces, and D1 and D2 are the distances from the pivots. So if I were to show that on a diagram with the forces and the distances labelled, we might have an object here and an object here, and let's suppose that this is exerting a force F1, we've got a force F2 over that side, and there are pivots in the middle, and the distances from the pivot are D1 and D2. Okay, so we can use that principle to solve problems. So let's take a case where we've got unequal masses on a seesaw, and we're trying to work out where we need to sit somebody in order to get the seesaw to balance. So I'm going to have a person over this side with a weight of, let's say, 60 newtons at a distance of 3 meters. And I'm going to have a person over this side with a weight of, let's say, a child with a weight of 40 newtons. And the question is, how far away should they be in order for the beam to balance? So we apply the principle of moments, which says that the clockwise moment has to be equal to the anti-clockwise moment. So sometimes it helps to think about anti-clockwise and clockwise using arrows like this. So I've got those the wrong way around there. Let's just swap those around. So we've got a clockwise moment going that way and an anti-clockwise moment going that way. So coming to our diagram, the 60 Newton force is going to be trying to spin things anti-clockwise if you think about its effect on the pivot in the middle, and the 40 Newton force is going to be trying to spin things clockwise. So 40 times by our unknown distance, we'll call that d, is going to be equal to 60 times 3, which is 180. And so our unknown distance is going to be 180 divided by 14, which is the same as 18 divided by 4, which is the same as 9 over 2, which is 4.5 metres. And if you think about it, that makes sense because we've got a smaller force, and so it needs to be at a greater distance from the pivot.